Good. Hi, everybody. Welcome to Compass Wednesday. It's my pleasure to introduce Will Downs. Will Downs is a fifth-year PhD candidate in the Department of Atmospheric Sciences, where he is advised by Dr. Sharon Majumdar. Before coming to UM, Will received a Bachelor of Arts in Geosciences and Computer Science from Williams College. He then worked for 2 years as a scientific programmer at Harvard University, where he supported development of the GeoChem atmospheric chemistry model. While at UM, Will's research has focused on tropical easterly waves and how these waves become tropical cyclones. In his spare time, Will enjoys paddleboarding and rollerblading, but he is currently on injured reserve after a brief foray into skimboarding. Take it away, Will.
Thanks, Aiden. So, as Aiden said, a lot of my research is focused on tropical waves and how they become tropical cyclones, and today I'm going to be presenting some work that we've done using machine learning to both identify and predict what tropical easterly waves are going to do. So, a little bit of background. Tropical easterly waves, I'll say TEWs sometimes, also known as African easterly waves or tropical waves. People call them a bunch of different things. There are these clusters of rain and wind, like on the right-hand side, that move through the tropics during hurricane season. A lot of them fizzle out without really causing any trouble to anybody. They give beneficial rain to tropical regions and just a little bit of gusty wind. But they're also the most important source of hurricanes, and especially major hurricanes in the Atlantic and in the Caribbean. And so we want to keep track of these waves then in the Atlantic and Caribbean because they can become hurricanes. But a lot of the existing algorithms we have for objectively tracking, automatically tracking these waves, they tend to lose these waves in the Caribbean. So figure on the right shows from two recent papers that use different but fairly similar objective tracking algorithms that use vorticity to identify where waves are. And in between the black lines on each plot is the Caribbean. And the thing to take away here is that there's a far lower density, much less coloration in the Caribbean. It seems like there are fewer waves. In reality, this isn't the case. Waves do become weaker and sometimes do fully decay as they enter the Caribbean due to frequent hostile background flow. And there's also ambient vorticity near Colombia that disrupts these vorticity tracking algorithms. So there are reasons that we don't see as many waves here in these trackers, and there are fewer, but there are some, and more than a lot of previous papers might suggest. So there is one source that does have a lot of waves monitored in the Caribbean. That comes from TAFB, which is the National Hurricane Center's Tropical Analysis and Forecast branch. And we want to use this human data set then to try to train a machine learning model to produce a longer record of wave and also intertropical convergence zone and monsoon trough activity, two other things that TAFB also keeps track of. They've been keeping track of these things since 2004 in a text product called the Tropical Weather Discussion, but we'd like to push that record back further in time to get a larger data set to analyze for research purposes. So can we train a machine learning model off of TAFB's labeled waves and ITCZ to then create a record going further back in time? And to do so, we're going to use a neural network. This is what our neural network looks like. It's called a UNet 3+. It's a little freaky to look at. Lots going on. But it can be summarized as such. At one end of the neural network, during training and during inference, where it's making its prediction later on, you input a bunch of gridded atmospheric data. In our case, we use stuff like wind, humidity, and IR from satellites. And you put in all these variables for a single time step. The network learns to extract relevant features for its task, which is identifying easterly waves or identifying the ITCZ, on a range of scales ranging from 25 to 2,000 kilometers in our case. The network learns how to best combine these features on all these scales to then output a probability map of where these waves are or the ITCZ. So we have two separate neural networks that we trained. One does waves, one does the ITCZ/monsoon trough and distinguishes between the two of them. So might not fully distinguish between them between the two networks at certain points. But here is what that kind of looks like overlaying over satellite imagery from July 2024. So in the blue contours, we've got tropical waves that the network's identified. These are probability contours, and you can see them processing westward across the tropics, off the coast of Africa, through the Atlantic and the Caribbean and into the Eastern Pacific. And we also label the axis of the ITCZ and monsoon trough in orange and red there. And generally the network, our networks perform well when verified against TAFB's data set. And so the rows here are not important right now, but what's notable is that performance-wise, darker coloration, more deep blue indicates better performance. Generally, the Atlantic and Caribbean, the network does fine at. East Pacific is more of a struggle zone. We think this is due to issues with waves being kind of taking on a different form in the East Pacific compared to in the Caribbean and Atlantic, where, as I will show slightly later, they're often more embedded in the ITCZ, and sometimes it's tough to distinguish and wonder about the distinction between what is a westward moving MCV embedded in the ITCZ versus what is a distinct tropical easterly wave. So if we look at verification plots, so this plot on the left shows in color, red indicates we have a higher density of false positives than we do true positives by comparison. On the x-axis in this plot, we have low-level curvature vorticity. And the y-axis, we have mid-level curvature vorticity, both gauges of how strong a wave is. So what we see here is that false positives tend to be weak. A lot more red coloration here, more weighted towards the bottom left where you have weaker vorticity. So there is some confusion where the wave seems to be labeling things sometimes that are not labeled by TAFB as waves. On the flip side, false negatives over here, meaning TAFB had something but the network did not, also confusion at the weak end of things. So there's clearly some ambiguity happening where there's not total agreement between the network and what it was trained on what is a weak wave versus is not. One other fun thing to note here is that up in the top right-hand corner, this indicates the strongest end of the tropical wave spectrum. And the network, this is saying that the network does not identify these very strong waves. And we think this is due to those waves end up looking a lot like TCs, which are not labeled as tropical waves ever in TAFB's data set, which is fair. So there's a certain point, which is kind of annoying for studying tropical cyclogenesis, where a wave becomes so strong and so close to being a TC that tracker just loses track of it, usually about 6 hours before it actually gets labeled as a tropical storm by the NHC. So we can also see that the network does assign lower probability, lower confidence to identifying waves that are weaker. So in the top row here, you have the composites of the lowest probability assigned by the network that something is a wave. And in the shading, we have meridional wind anomalies. In the contours, we have mid-level moisture anomalies. And in the lower rows, we have higher probability the network is more confident something is a wave, and you have a lot more anomalous moisture and a lot stronger anomalous wind. So the lower probability that a network gives is correlated to a weaker wave. And so this is it's interesting because it is a pretty direct relation, and it does give some gauge of how strong a wave is just by looking at the network outputs. But for doing our original goal, did we capture the waves in the Caribbean? Yes, we did. So the right-hand panel here is the outputs from the tracker, and clearly we do see more wave activity in the Caribbean. And we also are able to then produce longer continuous wave tracks than the other algorithms we compared to. And so you can see here in this plot, this is only showing waves that exist that are formed east of 40 degrees west. So out in the middle of the Atlantic, not yet in the Caribbean. And so out here, this is like the Eastern Atlantic near Cabo Verde. All the trackers are relatively similar in terms of number of waves captured. But as you progressively head west, especially once you get right around the Caribbean, things really fall off a cliff. And at this point, the tracker does have significantly more waves that it's kept track of even from before the waves entered the Caribbean. And it's nice to be able to then better track the fate of a wave as it comes off Africa, or the origin, say, of a tropical storm in the Eastern Pacific, that often those originate as tropical waves by Africa. So this is useful. We can generate longer wave tracks. And we can also say something about the characteristics of waves in different locations. So in this plot here, which is being blocked by the toolbar we couldn't figure out how to hide, this plot is showing relative vorticity. So orange shading is positive relative vorticity. The y-axis is vertical level, and the x-axis is longitude. And in these little gray boxes, I'm just highlighting where the Caribbean is. And so in the Caribbean, you have a much weaker vorticity signal than in the Eastern Atlantic or in the Eastern Pacific. You also have a drier mid-level composite for these waves in the Caribbean compared again to what you have in the Eastern Atlantic and Eastern Pacific. So Caribbean waves do exist, but they are weaker and they are drier. And as I hinted at earlier, we can also say something about the interactions of these waves with the ITCZ/monsoon trough. So on the left-hand panel, we have waves in the Eastern Pacific at any given date. What proportion of waves are not embedded in the ITCZ or monsoon trough? And that is given with this purple line here. And waves that are embedded in either the ITCZ or MT, and the green line here. In the right-hand panel plot, we have same colors, same color scheme, but a much larger difference between the fraction of waves that are not embedded in the ITCZ or monsoon trough compared to the Eastern Pacific. So East Pacific waves are more likely to be embedded, and when I say embedded, we do this just by saying the vorticity center of the wave is within like 100 or 200 kilometers of the ITCZ central axis. So we can say something interesting about the different climate characteristics of these waves and how they interact with the ITCZ. We can also talk about the ITCZ and monsoon trough themselves and what those look like. So here in this plot on the right, we have the day of year in the y-axis. So this starts at January 1st and goes to December 31st. In the x-axis, we have longitude. In blue, we have the monsoon trough exists at that longitude. In red, we have the ITCZ exists at that longitude. And so this is showing most frequently in a given year what is the mean state. Is it the ITCZ? Is it the monsoon trough? In the blank areas, is it nothing? But it's not really nothing, because in the blank areas, this is over land, over South America here, and at the edge over here over Africa. And this is just an area where we don't have training data. TAFB doesn't mark ITCZ or monsoon trough stuff over land. So this is not literally saying that there is no ITCZ over South America. But so you can see the westward progression of the monsoon trough as we enter Northern Hemisphere summer in the Eastern Pacific, really jumping out in mid-May and then staying pretty far progressed west of Central America all the way up until mid-November. In the Atlantic, you see something similar, but more delayed in timing, and it does not extend nearly as far west as what we see in the Pacific. And using this record of the ITCZ, we can say stuff about different annual trends and the characteristics of where the ITCZ or monsoon trough has been located. So 2024 actually set a record in our data set for the highest latitude of the ITCZ in the Atlantic. This is in the Atlantic between July 15th and October 1st, which we consider the peak part of the westward progression of the monsoon trough from the prior plot. So 2024 set a record for furthest north for the ITCZ in the Atlantic. It also set a record for furthest west extension of the monsoon trough from Africa in peak summer. And even without this big outlier in 2024, there also is a distinct trend westward in the monsoon trough. Again, this is from Africa in the Eastern Atlantic. Has extended further westward during peak summer months over the past couple decades, especially since the early mid-2000s. And so this is interesting because previous studies have shown a strengthening of the African monsoon associated with warmer sea surface temperatures with the AMO, but nobody has shown this before, that the actual monsoon trough has extended further westward from the African coast. So we've been able to create machine learning tools that help us identify tropical waves and also ITCZ and MT from data from the past. We've released our data sets of tropical easterly waves and the ITCZ MT going back to 1980. And now TAFB is officially using these operationally as on real-time data as analyst aids. Big thanks to Aiden, who was a co-author on this and really instrumental in helping parse through and figure out the intricacies of how NHC data works. So that's part one of the talk, outlining the data set that I'm going to be using for part two. Does anybody have any questions right now? Great. Okay, part two. So now we've got this big data set. We want to try to answer some questions about what governs the evolution of tropical waves. So there's been a lot of prior research into different physical mechanisms that govern easterly wave evolution in different parts of the world. In the Eastern Pacific, some processes that have been highlighted include instabilities of different easterly jets, a moisture vortex instability framework that's really gaining traction in the past couple of years, topography from Central and South America, either enhancing or causing a wave to form in the first place, and intraseasonal variations in zonal wind associated with the MJO or otherwise. In the Atlantic or over Africa, again, instabilities in easterly jets, moisture vortex instability framework, a lot of discussion about the influences of moist convection, specifically in the wave envelope, competing assessments of what environmental moisture does to a wave in different parts of the Atlantic or over Africa, whether it's helpful or a hindrance for a wave to be surrounded by a lot of moist air far away from the center. You also got convectively coupled Kelvin waves, which are definitely an influence pretty much everywhere. But the thing is, none of these factors are mutually exclusive. There's a lot going on that influences how these waves grow and decay. And there have been various papers that have taken a statistical modeling approach for looking at how easterly waves behave. But in almost all cases, these papers have focused on building a statistical model that relates how likely an easterly wave is to become a tropical cyclone. It would be nice if we could have a statistical model that gives predictions more on a continuum of wave characteristics beyond this binary of does it become a TC or does it not. So for this second part, our main question is what factors drive TEW evolution and uncertainty associated with that evolution across a variety of geographic regions and intensities. And to figure this out, we're going to use a neural network again. We're going to train a neural network to predict changes in convection and vorticity in waves, and then investigate what drives these changes in the neural network's predictions using what are called explainable artificial intelligence techniques, which you'll hear called XAI frequently. So I said we're going to predict convection and vorticity, correlated but very different things. So we want to predict convective organization and also the strength of the wind circulation associated with these easterly waves, because these are two important criteria for how we define what a tropical cyclone is. So at the very strongest end of the wave spectrum, I said we wanted to move beyond that binary, but it's useful to have variables that are relevant to how likely a wave is to become a tropical cyclone. So for our convection variable, we're going to be predicting the mean of the IR brightness temperature within 400 kilometers of a wave center. We're going to call that IR 400. For our vorticity variable, for measuring the circulation, we're going to take the average of a couple different levels of curvature vorticity within the wave envelope, and we are going to call this CV max mean. And we experimented with a bunch of different variables to come to these two. They ended up having the largest, they help distinguish the most areas of the Atlantic, Caribbean, and Pacific when you compare the distributions of waves that don't become a TC and waves that do become a TC. So these variables are relevant to cyclogenesis. They're not the only predictors that should go into a model predicting cyclogenesis, but they are relevant. So general setup for this, we are taking 6 hourly wave locations from the data set that I described in part 1 that encompasses the Eastern Pacific, the Caribbean, the Atlantic, and then also we've expanded the wave data set over Africa. We've compared results from our network, which was not trained with data over Africa, to conventional wave algorithms that identify tropical waves over Africa, and they're pretty similar. So we are also using tracks over Africa now. Going back, we're using 1981 in this case to 2023. And we're going to be making 1 through 5 day forecasts, so at 24-hour intervals. But we actually trained the network to simultaneously predict every 6 hours from 6 to 120 hours in the future. We found that this improved network performance compared to just training one network to predict 24 hours, one network to predict 48. So one network is predicting 20 different lead times. We have about 200,000 24-hour points and about 80,000 120-hour points at each end of the time range spectrum there. And then those samples are then split across training, validation, and testing phases for the network. But that gives us an idea of how many samples we're working with. For input fields, we're going to use 6 hourly reanalysis data and GridSat data on a 25-kilometer grid that is centered on our easterly waves. We're going to use different scalar variables, also like the initial values of the variables that we're trying to predict, our IR variable and our vorticity variable. We've got a couple 2D fields like IR brightness from GridSat. And then we have a bunch of 3D fields that come at different vertical levels listed here. And those 3D fields are our meridional and zonal wind components, our geopotential, and equivalent potential temperature, or theta E. We also trained a way simpler climatology model, I call it, which is only taking the initial values of the variables we're trying to predict, and then latitude, longitude, and what day of the year it is. And our neural network is different than the one we use to identify the waves in terms of structure, but pretty similar conceptually. We're going to be taking gridded atmospheric data, input in a 3,200 by 6,400 kilometer grid that's wave centered. So 3,200 in the latitudinal direction and 6,400 in the longitudinal direction. The network is going to learn to identify relevant features on progressively coarser / more abstract scales. Then it's going to take in the scalar variables and combine it with the core spatial data that it's developed, and then output a 50-member ensemble for each of our predicted variables for each of our 20 lead times. So it's actually spitting out 1,000 scalar values. And to train it to make an ensemble that is attempting to capture some measure of uncertainty while predicting an accurate mean prediction, we're using something called the continuous rank probability score. This has gotten attention, a lot of use in the past couple of years from various machine learning based weather prediction models. And what this does is it balances two terms when scoring how well a model is doing. The first term takes the mean absolute error of your ensemble members. So that term is more driven towards assessing, if you average out all your ensembles, how well is your ensemble mean doing? Second term takes the mean of the differences between each ensemble member and every other ensemble member. So that captures your spread, and that term encourages more spread. And these terms end up balancing out, where by training using this as our scoring metric, the network is simultaneously trained to reduce overall error, but also give an estimate of prediction uncertainty within this 50-member ensemble envelope for each of our predicted variables. Here's what an example forecast looks like. This is from the wave that became Hurricane Franklin in 2023. So on the x-axis, we have time starting over here. On the y-axis, we have in the top panel our curvature vorticity variable. In the bottom panel, we have our IR variable. And we were able to track this wave back over Africa over 2 weeks before it became Franklin. And so here in blue, we have our 72-hour forecasts for what the wave is going to do in our two variables. And we also give a 10th to 90th prediction envelope here in this plot of what our ensemble spread looks like. And then in black, we have the truth values for what these variables actually did. This was a good case for the model. It did well with predicting Franklin here at most lead times. There's also, you can see in its predictions of IR activity, what looks like a diurnal cycle in roughly 24-hour spaced out points here. So that's interesting. Here's a visualization that I really like of what the ensemble spread looks like at individual times for each of our variables. So vorticity is in the top again, IR is in the bottom. And you can see as the mean, which is in blue, bounces around. This is 72-hour predictions, but in the legend I accidentally wrote 24. The ensemble spread does change a lot. It's not like a fixed envelope around a mean. It does give an estimate that is not always symmetric and really changes in sheer standard deviations, sheer spread. So yeah, I like watching this, especially as, like at this point, this is an enormous spread. Even though the ensemble mean is pretty good, you have what is a very, very large spread relative to where basically every member is predicting its own very distinct value. So we create an ensemble that seems to have some worth in predicting different values and not solely focusing on the mean, though I will present some statistics about different skews that it has. So comparing performance just for 1 year, this is not a thorough comparison, but comparing how it performs versus the ECMWF's deterministic model from 2023. So here we average out, we just take the mean of our ensemble predictions. And so in blue, at each lead time, we have ECMWF. In orange, we have our climatology model. In green, we have our machine learning model, or our full machine learning model, I should say. And on the y-axis, we have root mean squared error, so lower is better here. So generally, it's pretty comparable to how the ECMWF does for this task at all lead times. And this is not meant to show any specific, like, oh, it's definitely better at 96 or whatever, because as I said, this is a smaller data set than we would like for gauging true performance. But in general, it does show us that reasonably we can look at the model and say it's spitting out something that's has some skill. It's not pure random noise. It is marginally better than this much simpler climatology model, but it is very interesting that the climatology model is so good on its own for this task. So our model has some skill, and so it's worth diving into what the predictions of this model look like. So here is a set of maps showing for 72-hour predictions of our vorticity variable. This is the mean prediction for a wave that ends up in a given location at 72 hours out. So in this case, values being plotted here are waves that are at 0 degrees longitude 72 hours in the future. And this is our predicted mean. This is our real mean across all of our testing dataset samples. And this is a difference in those then climatological values given by our neural network versus by reality. And what we see here is that the network in red coloration here consistently, or it has a higher bias in its mean compared to reality for predicting waves that are still over Africa here. And also for waves that end up over Central America, it predicts vorticity to be too high compared to reality. If we look at our IR predictions, and I apologize, not the best color scale for showing IR, but we see a pretty significant cold bias here shown in blue coloration in the Caribbean. So the model is predicting convection to be too strong, clouds are too cold for waves that are entering the Caribbean at 72 hours. We can also see in plotting, in this case, we have on the y-axis predicted change between the initial curvature vorticity value to the predicted value from the neural network. On the x-axis, we have the real change, how much did vorticity actually change by. And the blue line indicates a perfect prediction line where the neural network predicted the exact same value that really happened. And what we can see here is two different notable things. First of all, right around 0, so around things that don't change a lot of intensity, the model does have a bias to predict intensification. Not usually too large, but it does have a very noticeable bias there. There's also an underprediction bias for the largest intensifiers. So way over on the right here are the waves that intensified the most in reality. And you can see there's this dense concentration highlighted in this box where most waves that actually intensified a lot, the neural network underpredicted how much that intensification was going to be. And we've really tried to nip this in the bud using a bunch of techniques. This is the improved version after a lot of troubleshooting. Still stubborn, still having trouble with that. And in general, the ensemble thus has a bit of a under dispersion to it. So this is showing on the x-axis quantiles of our predicted values. So what does our total distribution of all our predictions look like? And on the y-axis, we have what percentage of real values end up falling in each bin. And ideally, you would have every quantile be exactly 0.01. So 1% of the predicted distribution should house 1% of the real distribution, but that is not the case. At each end, there is a spike indicating predictions that failed to capture reality. Reality fell outside of the ensemble envelope in either the low end or the high end. And if we try to look at any geographical information about are there any regions where this most frequently happens, for vorticity, there's not anything super distinct in terms of where our ensemble most often misses the mark. For IR, it's more obvious. There is this notable struggle region in the Caribbean, also parts of the Eastern Pacific. So our ensemble, it captures spread, but it doesn't quite capture spread. Doesn't account for everything, which is not an uncommon problem in ensemble forecasting, but it is also true of ours. So to try to get at what is happening behind the scenes in the model, what variables are driving changes, what variables are most important to the model making an accurate prediction, we're going to use a technique called permutation importance. In this, we're going to take some input variable, or it could be multiple input variables, or even a region of our input grid, and we're going to randomly shuffle everything across our different samples. So in this little diagram down here, we have samples indicated in each row and variables indicated in each column. And so we're going to shuffle variable 2, and now the values for variable 2 have been sent to a bunch of other samples, and nobody has their own original value there. So once we've shuffled, we're going to see how much error increased by shuffling this variable, and then repeat that, returning the original variable to where it was. We're going to repeat the same process for every variable or region of our input grid, which is what I'm about to show. And so what this gets at is if a variable or region is shuffled and error really increases, that means that region is important to making an accurate prediction on that data set for the neural network. If error barely increases, not as important. So what input areas end up contributing most to making correct predictions? Here, darker coloration indicates a higher increase in error when that part of the grid is shuffled. So this is for predicting curvature vorticity at 24 hours in the future. And what I'm going to do here is I'm going to tab through, and it's going to go out 24 more hours and show the changing map of which regions are most important. So 48 hours, 72 hours, 96 hours, 120 hours. So, wow, it's a lot better on my screen. Well, the main thing here is the darker coloration becomes more diffuse, less dark as you go further out in time. there's less focus on the actual wave envelope for when the model is making predictions further out in time, or I should say, the information from the wave envelope is relatively less important to making an accurate prediction the further you go out in time. This makes some intuitive sense because we do expect environmental influences to have a bit more of an impact as you go further out in time compared to just local scale, what's going on with the wave itself. There are also differences between waves of different intensities that were masked within that entire composite that I showed. So this is stronger waves for 72 hours out, dark colors near the center, and then weaker waves 72 hours out. This doesn't look like much. The main thing here is that, again, much less central importance, and also the color scale here is different. I did not change that. So darker colors here are actually lighter colors on the prior slide. So weaker waves, it's less important to have information about what the wave itself looks like for making a prediction further out in time, compared to when you have a stronger wave and you're trying to predict curvature vorticity of the wave. You care about what the wave envelope looks like more. If we do the same thing for IR, same deal, kind of a focus in the northwest quadrant here for predicting 72 hours out IR for strong waves, and then for weak waves, it's really doesn't care at all what's going on with the wave envelope. So we can also then look at this one rainbow plot of what vertical levels are contributing the most to making correct predictions of our variables. So here, each color indicates a different lead time. On the y-axis, we have each of our vertical levels for which we shuffled every single variable at that level to test how much error increased, shuffled them all at the same time. So, and all these values are scaled such that at a given lead time, whatever level increased error the most has a value of 1. So the variables are scaled relative to them, or the lead times are scaled relative to themselves and not across different lead times. And what we can see here is that lower levels guide predictions at all leads for predicting IR for our waves. There's also this fun step-down pattern of the importance of 200 hectopascal variables as you go further out in time, because blue here is 24, red is 120 hours out. And I'll show a bit later, but this ends up being related to decreasing influence of 200 millibar theta E as an input, so related to probably the temperature of the tropopause and how conducive things are to convection actually being brighter in the area. If we look at then what vertical levels are contributing the most to predicting correct curvature vorticity at different leads, at every single lead time at this nice, so looks like an Airheads extreme, it's 1,000 hectopascals is the leader for every single lead time. There also is a step-down pattern, 700 hectopascals going further out in time. Somewhat of a progressive increase in importance for oh, my internet connection is unstable. Whoa. So, unlike in the IR, where 200 decreases in importance to making a correct prediction as you go further out in time, for vorticity it becomes more important. And still looking into which fields it's honing in on there. If we then instead break down into which of our input variables, not levels anymore, but for a given input variable that is three-dimensional, we shuffle every level of that variable at one time. So here's our zonal wind, meridional wind, geopotential, and equivalent potential temperature. And then also we have all of our single level and scalar variables. Scalars end up never mattering really, but they are there. There are little notes there. What we do see is that for predicting IR, one notable thing is that this is gridded IR data, and we see that at 24 hours out, it's a lot more important than it is at later times relative to every other input. Makes sense. If you're predicting IR coverage for a wave 24 hours out, there is some relevance of what the convection looks like right now at this instant. Further out you go in time, you probably rely less on what clouds you have at any given moment. There's also a relative increase in the importance of our geopotential and equivalent potential temperature at longer lead times. These are variables we might think of as being more environmental influences, but still trying to drill down into which regions of those are most influential. If we look at the same thing for predicting vorticity, at all lead times, wind and either in the zonal or meridional direction dominates as our most important variable. This makes sense because, kind of like IR on the previous slide, winds directly contribute to what our vorticity variable is. So we do care, and kind of related to what I showed with the spatial plots earlier, the model really cares about what the winds near the center look like for predicting than what the winds will look like in the future. But there also is a relative, there is an increase in the relative importance of our non-wind variables like geopotential and theta E as you go further out in time. Also of total column water down here, topography and latitude here also become more important the further you go out in time. So again, there seems to be some indications that variables that we would think of as being more relative to the environment that the wave is in do become relatively more important compared to the actual wind structure of the wave for making predictions further out in time. So another technique that we're going to use, so all these previous plots I was showing were we wanted to see what causes error to increase the most when making a prediction. Here, we're actually going to look at just what makes the predicted value go up or down. So slightly different idea, but same concept of wanting to investigate what is driving the model and making its predictions. So we're going to use a technique called integrated gradients, in which you take some baseline sample. In our case, we use a mean composite of our waves. We're going to call that B, and it's got all its little inputs. You can imagine all its spatial variables, all its scalar variables, all flattened out to n inputs. You're going to take whatever wave you want to test out. We're going to call that X. And then we're going to increment in our input space between what B looks like and what X looks like. And at each little increment, we're generating a new prediction using our neural network, and then taking the gradient of that prediction with respect to every one of our input values. And so by doing this, we get an approximation of the full integral for our gradient of how our output is going to change with respect to each individual input. And this shows us then, in the end, how much the difference in a given input value, so say total column water 1,000 kilometers west and 500 kilometers north of a wave center, how much is that value in a given sample contributing to making the value go up or down relative to our baseline. So it's a way of gauging on a per pixel scale the importance of any given input. So here's an example of what that looks like. Again, we're looking at pre-Franklin from 2023. So on the top, or in the left column, we have meridional wind at 1,000 hectopascals. Green here indicates southerly, so moving northward. Purple indicates northerly, moving southward. And in the right-hand column, we have total column water. Greens are more moist. And so then in these bottom panels, we have our integrated gradients values for 24-hour predictions of our curvature vorticity variable and 120-hour predictions. So red here indicates that whatever value, say, we have here in our input data is contributing to a higher forecast value of our vorticity variable. Blue indicates it's contributing to making a lower final forecast value. And so here we see one little interesting thing, which is that there is this dipole between, there's positive contributions to the final predicted intensity at 24 hours from southerly wind here, but negative prediction or negative contributions here. And when comparing this to a bunch of other samples, seems like what's causing this negative discrepancy here near the center is that you have southerly motion at the surface in the wind field here. So this is not a strong, centered at all levels cyclonic signature. and you do have displacement of lower level winds compared to the mid-level center here. So some physical sense to that. Then if we look at a different time step, we have a different wind profile now, different moisture profile as well. Now we're seeing positive contributions from northerlies, which are these pink colors, that are located west of the TEW center. Now it has more of an obvious cyclonic pattern in the low levels. One interesting thing that we do see is that, so this is our 24-hour prediction score for total column water, 120-hour prediction. You actually have opposing signs in this general area northwest of the center for 24 hours versus 120 hours out. Potentially, this is due to, if you look at the moisture field here, is a pretty elongated area of elevated moisture that's maybe not the most conducive to strengthening vortex within 24 hours, but 5 days out, a lot of prior literature has highlighted enhanced moisture to the northwest of a wave as being conducive to becoming a TC down the line, and thus potentially relevant to just general strengthening of a wave. But if we go way out to when Franklin actually became a TC, I apologize I don't have continents plotted here, but this is right at the Lesser Antilles, so as Franklin is entering, or pre-Franklin is entering the Caribbean and becoming a tropical depression. There is a very strong contribution from this local cyclonic wind signature juxtaposition of our southerlies and northerlies here, contributing to a final increased value in our vorticity variable. Well, there's a lot of confounding stuff when trying to analyze these outputs. So this is our 24-hour contribution plot. So it's saying, here's the score it's giving for the contribution from each of these points in the grid to the 24-hour prediction is for total column water. And if the model were actually totally like physical, we would expect there to be no influence from something, say that's 3,200 kilometers east within 24 hours on the actual dynamics at the center of the wave. A lot of correlation going on. There's so much data going into these kinds of models and there are a lot of fields in the atmosphere that we know from being atmospheric scientists. They are correlated with one another across space, across time, across different derivations of different variables. And so the model's not always going to be picking up on directly like, oh, this is most dynamically relevant. It picks up on different setups that have high correlation in the past with making a good prediction, but aren't necessarily giving us a physically reasonable result. So it's a risky business trying to interpret physical impressions from some of these, but there are signals we can see in some of them, in some of these plots that do resemble prior literature and what we know of wave dynamics. And in addition to correlation between different fields, we also have an issue that if we go back to what I said about how we're predicting every single lead time from the same network. So the model's taking all of its input fields and it's jumbling them up, and then it spits out at the very end, it separates every lead time. That means that it's going to have the same inputs going into every lead time at once, and it's going to inherently learn that information that's relative at, say, 6 hours out is also going to be relevant to predicting 2 hours out or 12 hours out, because our variables that we're trying to predict are autocorrelated to a certain extent, especially our vorticity variable. So vorticity of a wave at 12 hours out is going to be related to the wave at 18 hours out, and in the end, several days out, it's a pretty good predictor on its own of what wave is going to do. So for that reason, we've observed that our model increased in performance when we chose to take this approach, but when comparing these kinds of signals we see in what the model seems to be using in our input variables and input space, there's a lot of cross-contamination in the signals between different lead times. So there's a footprint, say, of predicting 72 hours. What's important at 72 hours is then also going to be used to some extent to predict what vorticity is going to look like at 24 hours out. So just a fun confounder to trying to interpret all this. We can try to break down then what variables are most important at certain lead times on an individual scale and see how that changes as you go further out in time. So this grid here, darker colors indicate a given 3D variable in this top matrix here, and then vertical levels on the y-axis. And then here are single level and scalar variables down here. Darker colors indicate that for any given sample, that variable tends to have a higher importance compared to all the other variables. And we do end up seeing, I'm going to tab out through time, but V1000 at 1,000 hectopascals, total column water, topography, 1,000 millibar geopotential, and 500 millibar theta E end up being pretty consistently important across all lead times. I'm going to tab back through time here, see the little text jump. So there is some consistency across lead times for different variables, but there are also changes. For example, the importance of theta E shifts more to lower levels, and zonal wind increases in importance in a column sense, which we also saw in the permutation testing earlier as you go further out in time. If we look at IR instead, our consistently most important variables end up being 1,000 hectopascal geopotential, 850 hectopascal geopotential, total column water, and topography. And as I alluded to earlier, and as we saw in the permutation testing, the importance of 200 hectopascal equivalent potential temperature up here and gridded IR down here are going to decrease as we go further out in time. Lighten up. So there are changes in what the network cares most about at different lead times, but there are plenty of similarities. I apologize for the label at the top being cut off here, but here we're going to then look at what is the average contribution across all of our samples. I should say this is only for 2023. This is very computationally cumbersome to do, so we don't have our whole testing data set done yet. But in this case, what this is showing is for predicting curvature vorticity at a 24-hour lead time, what is the average relative importance, so darker is more important here, of total column water at a given location for making that prediction of vorticity. And so if we go forward out in time, 48 hours, 72 hours, 96 hours, 120 hours. Again, less focused in the center as we get further out in time. And this is really faint on the projector, but there is a more diffuse signal that resembles potentially more different either ITCZ or moisture connections between a wave and areas to its east. We also see this northwestward shift, or focus in the northwest quadrant, I should say, the further out you go in time of where moisture is most important. This is, again, known from literature as being an important region for wave development towards becoming a tropical cyclone. So this is, again, can't say causation here, but it's good to see that what we have here resembles prior studies into what drives waves. And there are also variations in the footprint of total column water when we discriminate between waves that are in our top 10% of strength initially for vorticity versus our bottom 10% of vorticity initially. So there are differences in strength as to which areas are most cared about, and that ends up being that in the weaker cases, there is more of a diffuse signal resembling connections either to the ITCZ or a trailing disturbance perhaps, and moisture there. So we've created a prediction network that is skillful at predicting convection and vorticity in these easterly waves, but we still have a lot to do with interpreting what exactly is going on under the hood and trying not to over-interpret what's going on under the hood. Need to explore regional differences, which I skipped over here in terms of which variables are most important. And we also need to explore what's governing uncertainty, which is one of the main goals of this. So we can directly estimate or gauge how different variables affect spread, for instance. Just need to do that. And we're also working on idealized modeling of some of these more complex wave cases that involve mergers between multiple easterly waves. So that's it.
Hey, Will. I want to ask about how your ensemble is generated,
Yeah.
right? Well, how is the ensemble generated?
Yep.
Can you tell me?
I can tell you that it is not a specific layer in the model. I know you asked this in the spring.
Yeah, so it all seems, yeah, this is coming back to me now. So,
So it's not a specific layer in the model that's like doing noise injection, which is how like a lot of
you
these,
could add random noise and then you would get an
you
ensemble.
could add random noise. That's another method of creating an
So
ensemble.
that's not what you're doing.
That's not what's happening.
Okay.
And what it is that this is going to sound dumb, but you say you have all these different weights that can be optimized, and at the end of that, I want you to give me an ensemble. And somehow it's giving you an ensemble because that is its target at the end. Now, why I've tried actually using noise as a different mechanism. In the end, that made things worse, I think, because my data set is a lot smaller than some of these global models that are using noise injection as a means of perturbing. But what I can say is that there's no specific layer that's making the ensemble work. It's a cumulative effect of every single layer being optimized to, at the end, predict an ensemble.
So it's predicting 50, I guess, ensembles, 50 outputs at once.
Yes.
And yeah, but how does it know to make them spread? There's that function, right? Basically.
Yeah, because during training,
Okay, so
if
it's a
it-
single model that produces 50 values, right? That maximize basically your CRPS.
yes. Although in reality, it's one model doing that for 20 different lead times for 2 different variables, but they're all assessed separately. So the ensemble from 6-hour vorticity is not contaminating the ensemble of 72-hour IR, for instance, in scoring.
Okay. All right.
Okay, so you used integrated gradients, right? And the permutation importance. Those are your 2 XAI methods.
Yeah.
Why did you choose those 2, and what would you pick if you could pick a third?
Well, I picked those 2, generally because they fall into these 2 slightly different categories of permutation testing. Says how much does our error change, which is good for knowing what's driving correctness. The integrated gradients is falls under attribution, which its intent is to directly measure what is actually getting propagated through the network to create a final output. I'm not familiar with for testing that first thing, for testing error. I'm not really sure what other methods are out there. For attribution testing, there's a lot of different, somewhat similar methods. There's a lot of stuff with Shapley values, which are something from game theory that got developed in the 60s, that it's the same idea where you're trying to say, for every input, what's it worth to me for making the final value. In the end, I tested out some Shapley functions. Integrated gradients was what I was able to finally get to work, because I was having some issues with those. It's also relatively, compared to some other methods, it's expensive, but it's not that expensive. But it would be good. We do see some, as I talked about, some overlap in the permutation side and the attribution side of identifying what variables are key in some sense. And that's good, even though they're testing different targets. It would also be good to test another attribution method, which I have tested a Shapley method, but I didn't show, that broadly showed similar results of what matters to this model for making good. So some sort of Shapley method.
Cool, thank you.
Thanks, Will. That was really awesome. My question, I guess I have two questions. One relates to the idea of the signal of the tropical waves of the Caribbean that you're trying to fill in that gap. And one of the errors that we see in the global models like the GFS is erroneous vorticity aggregation from Columbia and like orographical vorticity. Were you able to sort of address that error in your tracker model, or see if there's like maybe an amplification of the waves in that area?
Good question. Yeah, I'm trying to remember. So I did have composite plots showing So I did have composite plots that resembled this, not on a probability scale, but on just general time of year scale, just what do waves look like in different regions, which is also what this vertical composite was aiming to look at. That area is around 80 degrees west. We do see in our mean composite an increase in vorticity of these waves. I have not dived into separating that from other general vorticity in the area. So,
Yeah. Thanks.
What was your second question?
I guess I'll just ask really quickly. It seemed like mid-level moisture was a really important variable. Could you
Yeah.
kind of unpack that? Like in terms of just the importance of that variable versus other variables? Am I incorrect or in thinking that, or did I interpret your slides
No,
correctly?
you're right. I haven't dived too much into it, but presumably it's related to entrainment and from the environment of what's going into a wave, as we would expect. One interesting thing in my model is that total column water ends up being more important than any individual level of moisture, but in some cases, at certain lead times, mid-level moisture does dominate out of all the different levels of moisture. At other lead times, it's, for whatever reason, low-level theta E is what's getting flagged the most. And I have not investigated why that is.
Thanks.
All right, on Friday, we have Samantha Medina with her 1-hour OCE Compass presentation. And on the back end of the Thanksgiving holiday, we're fortunate enough to have Dennis Hansel and our very own Roland Romiser presenting as part of our Compass faculty series. Thank you again, Will.